Okay, this is the Chapter 8 chemistry lecture. Hopefully you've been able to print off the Chapter 8 notes that are in the Files section on Microsoft Teams. And we're just going to go through this. Now this Chapter 8 and Chapter 9 doesn't have any math in it. So some of you will really like that, but there are a lot of, there's a lot of vocab and a lot of things to go through in the notes. So the notes take up a lot of real estate. So this chapter is about molecular structure. And some general facts about molecular formation is that the electrons play the most important role. All right, so maybe you'll highlight or underline electrons. They play the most important role when atoms join together to form molecules. Atoms never really get close enough for their nuclei to interact. The only electrons that significantly affect the chemistry of an atom are those farthest from the nucleus. The farthest, not the inner electrons, but the outermost electrons, and those are called valence electrons that I have bolded and italicized here. The electrons farthest away from an atom's nucleus, which are usually in the highest energy level. We talked about energy levels in Chapter 7. Valence electrons, sometimes described as those located in the outer shell. So outer shell would be a good word to highlight. An atom's chemistry, or willingness to react with other atoms, is mostly determined by the number of valence electrons. So how many valence electrons does it have? That determines how reactant it is. So atoms in the same column of the periodic chart have the same number of valence electrons and thus a similar chemistry. Now I'm not talking about all of the columns on the periodic chart. I'll get a periodic chart out in just a second. The noble or inert gases, that's the far right, column 8A. All noble gases have what we call a full outer shell. They can't take on any more electrons. So for this reason, they rarely react with other substances. So for example, let's take a look at neon. Okay, neon number 10. Its electron configuration is 1s2, 2s2, and then 2p6. Okay, so it in energy level 2, its outermost energy level, it has 8 electrons. For argon, all right, its argon is 1s2, 2s2, 2p6. All right, if you want to follow along, argon right underneath neon here at number 18. 3s2, 3p6. Okay, so you can see it has 6, 6, 12, 13, 14, 15, 16, 17, 18 electrons. Its valence electrons, the outer shell, its highest level, energy level, is 3. Okay, so it has 8 electrons in its outer shell. So see how there's 8 in neon's highest energy level, 8 in argon's highest energy level. That's called the octet rule. Okay, remember octagon, 8 sides. Most atoms strive to attain 8 valence electrons. There are some exceptions. So atoms with with less than 4 electrons, like hydrogen, helium, lithium, beryllium, they try to attain only 2 valence electrons. Okay, boron is an oddity. It strives to attain 6 valence electrons. Okay, we won't be dealing with boron here in high school general chemistry. For the elements in the S and P blocks on the periodic table, the column number is equal to the number of valence electrons. So we're only talking about the S and P blocks. So I want you can go ahead and mark out this upper number, that 1, 2, and then over here in P block 13, 14, 15, 16, 17, 18. We are worried about the number that has the A behind it. So 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. That number, 1, 2, 3, 4, 5, 6, 7, 8 in this column tells you how many valence electrons are in the outer shell of each of these atoms in S block and in P block. Okay? The exception is helium. Helium only has 2 valence electrons, okay? But neon on down would have 8. Fluorine to astatine has 7. Oxygen down to polonium, 6, okay? And so forth. Beryllium down to radium has 2 valence electrons. So that column is super important in determining how many valence electrons. All right, back to your notes. Lewis structures. Lewis structures are an atom's symbol surrounded by dots. The dots represent valence electrons. Lewis structures are sometimes called electron dot diagrams. Okay, so Lewis structures for ionic compounds. For ionic compounds, metals try to gain electrons to achieve a full outer shell, and non-metals try to gain. Metals try to lose. We'll get there in just a second. Let's go back up here to 8.1. So on your own, 8.1 is on page 251. All right. So we'd want to draw the Lewis structure, also called the electron dot diagrams, for calcium, silicon, and astatine. All right, so, this is Chem Chapter 8, Lecture 1. Okay, so our first one is calcium. Well, how many valence electrons does calcium have? Well, calcium is in column 2, column 2A, all right? So it has 2 valence electrons. And the way you draw those dots, start at the right and go clockwise. So 1, 2. That's all it is. All right, B is silicon. So let's find silicon on the periodic table. Okay, it is here in column 4. So it has 4 valence electrons. Start on the far right. 1, 2, 3, 4. That's the electron dot diagram. All right. Give me a lot of these on the test, right? And then the third one is astatine. Okay, astatine is in column 7. All right, number 85. So you do it like this. 1, 2, 3, 4, and then we put a double right there. 5, 6, 7. So the only side that has a lone electron is the top one. All right, so just keep going around clockwise, fill in 4, and then start putting the electron, what we call the electron pairs after that. Now I got ahead of myself just a second ago. For ionic compounds, nonmetals, highlight nonmetals and gain. Nonmetals try to gain electrons, and then highlight metals try to lose electrons, okay? So our example is potassium bromide, KBr. So let's put this there at the bottom of page 1 in your notes. So the electron dot diagram for potassium is in column 1. So it has 1 electron in its outer shell. Bromine is in column 7. So it has 7. 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell, what we call valence electrons. Well, nonmetals, potassium, everything on the periodic table wants to be like a noble gas because they have a full outer shell. That's the most stable. Potassium's right over here, okay, right over here. If it loses 1 electron, loses that one it has in its outer shell, it'll be like argon, and it'll be more stable. So metals, potassium wants to lose that electron, okay? Bromine, here in column 7, wants to be like krypton. It needs to gain an electron to be like krypton, and then it's in its most stable place. So potassium loses an electron. Bromine has an open slot to gain an electron. So what that means is if you lose a negative charge, potassium becomes positive by +1 charge. And bromine becomes negative. It gained a negative charge, so suddenly it has overall a negative charge. Opposites attract. So these are now going to have a pull towards each other. Since those opposites attract, that plus and that minus, that's what makes this an ionic compound. Electrical charges keep the potassium and the bromine together. All right, let's look at the top of page 2. An ion that has gained or lost electrons has thus become electrically charged. So let's draw out the electron dot diagram for CaCl2 in that example 2 area there. So we have calcium chloride. Now calcium, if you look at the periodic table, calcium is in column 2, so it has 2 valence electrons. Chlorine is in column 7, so it has 7 valence electrons. Calcium is a metal, right? Calcium, right here, it wants to be like argon. It wants to lose 2 electrons. If it loses 2, it'll be stable like argon, okay? Chlorine wants to gain 1 electron. It wants to go from 7 to 8 valence electrons. Okay, so calcium can give up 1 of its valence electrons to a singular chlorine, but what about this one? Well, we need a second chlorine. So if we can get a second chlorine, and they are always available, then calcium can give its second electron up. Okay, so what happens is that calcium ends up becoming, it loses 2 electrons, so it has a 2+ charge. You do need to put the plus and the minus second if there's a number. You'll learn about why in chapter 16. And this chlorine becomes -1 charge, and this one becomes a -1 charge because it gained an electron. So what happens is the atoms start exchanging electrons until all of them attain an ideal electron configuration. So this table, you don't have to memorize this. Really, you just learn it. It's just from the periodic table. If you're in column 1, you have 1 valence electron. They're metal, so they want to lose 1, except for hydrogen. But hydrogen just wants to lose 1, and it gains a +1 charge. And you can go down all of these. And when you get to, we mostly deal with column 1, 2, 3, 5, 6, and 7. Typically column 4, which is carbon, those form covalent compounds. All right, so column 5 wants to gain 3, column 6 gain 2, column 7 gain 1 electron, and they end up with negative charges. Okay, so our rules for, I'll give you a blank sheet of paper here. Wrong one. Sorry about that. All right, our rules for determining the ionic compound formulas. If the charges for each atom have the same numerical value, such as they're both 1 or they're both 2, then the subscript for each ion can be dropped. Okay? I'll show you what I mean in a second. If the charges have different numerical values, we drop the plus and minus signs, switch the numbers, make them subscripts. Let me work some for you so that will make sense. All right, you've got an open slot there at 8.2 in the book. Flip over to page 257. Look at us go. So 257 says determine, or 8.2 says determine the chemical formulas for the following: calcium chloride, potassium sulfide, aluminum nitride, and magnesium phosphide. All right, well, I'm going to show you how to do it based on the periodic table. Okay, so 8.2a, we have calcium chloride. Okay, so first of all, calcium is in, we've used it a lot already, it's in column 2, wants to lose 2 electrons, that would give it a 2+ charge. Chlorine in column 7 wants to gain 1 electron, so it will have 8 in its outer shell, so that would give it a minus charge if it gains 1 electron. So what you do is, this is just a 2 since they're different. You take that 2 and you make it a subscript. And you take that 1 and you make it a subscript. So it's calcium, CaCl2. You just take that superscript, make it a subscript, forget about the plus and the minus. So that is the formula for calcium chloride. Let's do another one. The next one was potassium sulfide. All right, potassium is K, sulfide is S. Potassium in column 1 wants to lose 1 electron so that it can be like argon. All right, if it loses an electron, it'll have a plus charge, +1. Sulfur is in column 6. It wants to be like argon. It wants to have 8 valence electrons. So to do that, it has to gain 2. If it gains 2 electrons, that would give it a 2- charge. So we're going to take those superscripts and flip them and make them subscripts. So you would have K2S. All right, the next one is aluminum nitride. All right, so we've got aluminum and then nitrogen. Aluminum is metal. It wants to lose electrons. It's in column 3. If it loses those 3 electrons, it can be like neon. All right? If it loses 3 electrons, it would have 3 extra positive charges now. The nucleus, the protons are positive, so you lose 3 negative charges, you have a 3+. Nitrogen is in column 5. It wants to gain electrons. It's a nonmetal, so it wants to go to 1, 2, 3, get to neon. So if it gains 3, then it would have a 3- charge. But I told you, if we were to do the big switcheroo here, we would have Al3N3, but when they're the same, you get to drop the subscript, so it's just ALN. All right, and D is magnesium phosphide. So we have, well, let's write it out. Okay, magnesium is Mg, phosphorus is P. So let's find magnesium on the periodic table. It's in column 2, 2 valence electrons, and it's a metal. It wants to lose those 2 valence electrons so it can be like neon. So that would be a 2+ charge. Phosphorus is in column 5. It is a nonmetal. Nonmetals gain. It wants to gain 3. So it can 1, 2, 3. If it gains 3 electrons, that would be 3-. Now we're going to switch those superscripts. Mg3, P2, right? I'm going to bring that there, bring that there. So that's how you do ionic compounds. All right, pause the video if you need to, and we will move on to the next thing. All right, if the transition metals are what we call the D block metals. So remember from chapter 7, D block is this big block right in here. And you can't use the column to tell how many valence electrons that they have, okay? So in order to find how many valence electrons, and it's called something called oxidation states, but we get to that in chapter 16. The number of valence electrons will be given to you by a Roman numeral. So highlight that Roman numeral there. So let me show you what I mean. In 8.3 is on page 258. All right, so I'm not going to bring the book into view. Hopefully you've got yours there. A, we have iron, and then the Roman numeral 3, fluoride. And we want to know what is the compound for that, all right? Well, or the chemical formula, excuse me. Well, iron, the 3 tells you that it's a metal, it's a 3+ charge. Remember, metals become positively charged, they lose electrons, so that's what the 3 means. Fluorine, we can figure out from the periodic table. So that Roman numeral will always be with the metal. All right, fluorine is in 7, column 7. How many electrons? It's a non-metal, it wants to gain. How many? 1. Goes over 1 to be neon, so that give it a -1 charge. So after the switch, it would be Fe, F. Man, that's terrible. Sorry about that. Fe, F3. Right? Doink. Doink. All right, B is copper 1 iodide. Okay, copper, the Roman numeral tells you it has a +1 charge. Iodine, we got to find it on the periodic table. Here it is, column 7, non-metal, wants to gain 1, so that would give it a minus charge. It's the same numerical charge, so it's just Cu I. And then C is manganese 3. Let me write it out. Sorry about that. All right, manganese 3 oxide. So manganese is Mn. The Roman numeral tells you it's a 3+ charge. Oxygen. Oxygen is in column 6. All right, so how many electrons does it want to gain? It's a non-metal, so it wants to gain. It wants to gain 1, 2 to get over to neon. So that'd give it a 2- charge. So you have Mn2O3 after you switch, do what I call the big switcheroo. All right. So pause it if you need to, and we'll go on to page 3. All right, page 3 is called, that's page 5, sorry about that. Page 3, we're going to go over periodic properties, all right? And this is not a hard concept. You can look at the periodic table and tell some major things about an element. So ionization means the process by which an atom becomes an ion by gaining or losing electrons. That's what we've been talking about the whole last 2 pages of notes. Our first periodic property, and it's talked about on page 260. All right, so turn there real quick. But our first periodic property is ionization potential, and that's the amount of energy needed to take away an electron from an atom. All right, so another way to put that, right underneath, right in here for ionization potential, how tight or how tightly an atom holds on to its electrons. All right? How hard is it gripping? Okay? So if you want to know, just draw over to the right here. So over to the right, draw a rectangle that kind of looks like the periodic table. Ionization potential, if you start with the lowest down here in the lower left corner at francium, ionization potential increases that way and increases that way. So increases and increases. So the highest ionization potential is up here at helium, and the lowest ionization potential is down here at francium. Okay, so helium really holds on tight to its electrons. Also fluorine. It's hard to get electrons away from helium, fluorine. Francium's taking its electrons to goodwill. Just doesn't care. Okay, so that's ionization potential. So let's look at 8.4. So this is page 260. All right, it says order the following atoms in terms of increasing ionization potential. So it lists iodine, ruthenium, tin, and rubidium. So which one has the highest, which one has the lowest? If it's increasing, we're going from low to high. All right, so of those four, here's iodine way over here. Rubidium is way over here. Ruthenium kind of in the middle. And then tin is right here. So they're all on the same row. All right, so to the far left has the least ionization potential. So the way that I want you to write this out is the lowest is rubidium. Then we go to ruthenium. Then we go to tin. And then we go to iodine. Okay, again, it increases left to right. So rubidium, ruthenium, tin, iodine. Let's look at 8.5. So we're given potassium, lithium, cesium, and francium. And we want to know which most readily gives up its electrons. Well, francium's in the lower corner. It has the least ionization potential. It holds the least tightly to its electrons. So it would be francium. All right, pause video if you need to, and we'll go on to the second periodic property. This periodic property is electronegativity. And think of electronegativity as desire for other atoms' electrons. All right, how strongly the official definition is how strongly an atom attracts electrons to itself, okay? And so desire for other atoms' electrons. If we draw another rectangle to represent the periodic table, it's the same thing. We're increasing from bottom to top and then increasing from left to right. So again, helium and fluorine have the most, francium has the least. So just like ionization potential. Let's look at 8.6. All right, 8.6 is on page 262. And we're given magnesium, phosphorus, sodium, and sulfur. And the question is, which element desires electrons the most? Well, let's look at the periodic table. Magnesium, way over here to the left. Phosphorus is over here. Sodium, way to the left. Sulfur, over here to the right of phosphorus. So the one to the furthest to the right and furthest up would be sulfur. 8.7, order the following in terms of increasing desire. They give us fluorine, astatine, chlorine, iodine, and bromine. Those are all in column 7, and they have a name. They're called the halogens. Okay. So the highest electronegativity is up here at the top, and the lowest is down here at the bottom. So if we order them in terms of increasing, we would start with astatine, and then we go to iodine, then bromine, then chlorine, and then fluorine. Those with a high electronegativity are very reactive. You'll see them in a lot of different chemical reactions. All right, one more periodic property, so pause the video if you need to. Our last periodic property is atomic radius. And when you think of radius, you think of just a circle, right? So if you want to think of an atom with a nucleus and electrons orbiting, think of it as a circle. Atomic radius is just how big is the circle? Okay, physically, how big is the atom? So the official definition is the radius of an atom from nucleus to outermost electrons. Okay, well, if we were to draw our sample rectangle that represents the periodic table, it's exactly opposite of the last two. It increases going right to left. The atoms get bigger. And from top to bottom, they get bigger. So that down here is the biggest. And up in the far right corner is the smallest, has the smallest circle. All right, so 8.8 says which element is the largest? Magnesium, phosphorus, sodium, or sulfur. All right, well, let's find them. Sulfur's right here. Magnesium's way over here. Sodium is to the farthest to the left. And sulfur's over here. Okay, the farthest to the left is sodium, so sodium is the biggest. All right, and our last on your own for the day, we have fluorine, astatine, chlorine, iodine, and bromine. We want to order them in terms of increasing, so smallest to biggest. All right, so the smallest of those is going to start, we're going to start with fluorine and then go down. So it's going to be fluorine, chlorine, bromine, iodine, and then astatine is the largest. Okay, so that does it for today's lecture. The homework that goes with this lecture is review questions, page 283, 1 through 8, and practice problems, page 284, 1 through 6. And I will talk to you next lecture.